And the final talk will be given by Win again, who will pretend to be Vasily.
Yeah, unfortunately, Vasily wasn't able to be here this afternoon, and Win agreed to step in.
An ancient massive merger revealed by Gaia Data Release 2. We've returned to the galactic halo. So here we see the Milky Way galaxy at the center, and an enormous ink splot, which is the dark halo of the Milky Way. And of course, the dark halo has a stellar tracer. And so we're interested in both the stellar halo and the dark halo. We're interested in its mass, its shape, and its clumpiness. And the reasons for that are given below. They're controlled by the nature of the dark matter particle, whether it is warm, hot, or cold. It's also dependent on the accretion history of the Milky Way, how the material, how the dark matter, how the stars in the halo were assembled, and therefore the coupling of the dark matter to the baryons. And this leads directly to consideration of the first stars and the first galaxies and the nature of gravity. So that's why we're interested in the galactic stellar halo. At the beginning of the talk, we shall be interested in the velocity ellipsoid. So I can clearly look in position space at, say, positions of stars, as shown on the left. I can also look in velocity space. So in spherical polar coordinates, I can clearly work out a radial VR, and then an azimuthal v phi, and an angular or latitudinal v theta component, and I can plot the locations of stars in velocity space, and a cross-section might be as shown with a radial velocity and an azimuthal velocity, and very often I can take the azimuthal and angular velocities to be the same, so I imagine rotating this figure about the radial velocity axis. So what's an interesting parameter to consider is the anisotropy parameter, which tells me about the shape of the velocity ellipsoid. And conventionally that's indicated by beta is equal to 1 minus the sum of the two angular velocity dispersions divided by 2, and then divided by the radial velocity dispersion. So it's 1 minus the tangential motion divided by the radial motion. So what's on the menu? If I were to consider an isotropic model, then my distribution in velocity space would be like a meatball. VR, v theta, and v phi would have equal weighting. If I have a tangentially anisotropic velocity dispersion, so now beta is less than 0, and the stars have predominantly circular or near circular orbits, then I would get a burger, because the VR axis is short and the two angular axes are long. And the final example is a sausage, and this occurs when I have strong radial motions. So the VR axis is long, and then the two angular axes, v theta and v phi, are small. And the more positive I make beta, the more the stars are dominated by radial orbits, and so the more I have turned my sausage from a fat frankfurter into a narrow chipolata. And one of the first discoveries that was made with Gaia DR2 is that there is a sausage in velocity space. And so we can do this by studying the stellar halo in 7 dimensions. Here is the data. So this is a sample of Gaia stars, again cross-matched with SDSS. So it's of the order of 100,000 main sequence stars in a 10 by 10 by 10 kiloparsec box centered on the sun. And here, of course, is the data, the position on the sky, the two angular coordinates, the color and the magnitude, the proper motion in RA, the proper motion in DEC, the line of sight velocity and the metallicity. and I can convert that into galactic position and galactic velocity and metallicity. And then I can plot up the distribution of velocities as a function of height above the disk, higher and lower, and as a function of stellar metallicity, low in the halo, and then higher metallicity, higher in the halo. So these metallicities are between minus 1.3 and minus 1, whereas these metallicities go down to minus 4. And we can see by eye that we're moving from the land of the meatball to the land of the sausage. Let's look again. So these are very metal-poor stars in the halo, and I'm plotting the radial velocity versus the angular velocity, and I see a round distribution. At the same location in Z, I've done the same, but for a much more metal-rich sample, again, comparatively metal-rich stars in the halo. And I see a sausage. In fact, there's some disk contamination here, you can see, because there's a pimple on the sausage corresponding to a rotational velocity of about 200 kilometers a second. And so I can formalize this by plotting either the velocity dispersions as a function of metallicity or the anisotropy parameter that I just introduced as a function of metallicity. And this is done here for different heights above the galactic plane, but you see the self-same story. We move from the land of the meatball very sharply to the land of the sausage. The anisotropy parameter can only reach beta equals 1. That is when all orbits are radial. And so these are astonishing values for the anisotropy parameter of the stars, about 0.9 to 0.95. These are all stars moving on very, very radial orbits. How could this have come to pass? So the suggestion was made in this paper as to how this could have happened. We can see it also when we look in action space. So I'm now plotting cross-sections in action space for metal-rich and metal-poor stars, and here I've taken the difference. So it's the difference plot that is most interesting. Red tells me where the metal-rich stars in the halo are occurring, and they're occurring at large values of the radial action and low values of the azimuthal action. A same story of very, very radial orbits that are not rotating very much in the galaxy. How do you build this? So the claim is the data betray evidence of a head-on collision between the Milky Way galaxy and another galaxy, which has outrageously been called the Sausage galaxy, about 8 to 10 billion years ago. And the evidence comes from studies of the stellar halo stars in velocity space and in action space as a function of metallicity. And here is an artist's impression of the Milky Way galaxy and the Sausage galaxy. So we can now look at, in a little bit more quantitative manner, and this is work done by Asif Fatahi at Durham. So this is now looking for such things in the Auriga simulations. So here are the Auriga simulations, and they're plotted for stars in this range, that is comparatively metal-rich, and in a very narrow range of vertical positions. We've plotted them in the plane of anisotropy versus contribution of such stars to the whole halo. And for the Milky Way, we know that the contribution of such stars in this range of metallicity moving on very radial orbits is very high. It must be of the order of 80 or 90%. And I've just shown you that the anisotropy parameter is very extreme. So the Auriga simulations that roughly match the Milky Way are in the box, and maybe the best match of all is shown by the pink splotch. And here we're looking at the assembly history of all these simulations. The pink splodge is what looks like the Milky Way, and the blue is the average of the Auriga simulations. And you see the pink splodge suffered a large accretion event about 2 or 3 gigayears after the Big Bang. So this is consistent with the picture that the radial component was made by a very early accretion event. And of course, we can go further with the simulations and look. Here I'm showing the red-filled pool balls are the Milky Way analogues, and I'm showing them in the plane of stellar mass of the progenitor versus fraction of the radially biased component, the sausage, and merger time versus stellar mass. So it's the right-hand plot that's probably the most interesting, and it's telling me that the progenitor was a big progenitor, probably, of the order of 10 to the 9 solar masses in stars, and the merger time is between 6, 8, 10 gigayears ago, as judged from the Auriga simulations. So let me now give some further evidence. If this really was such a big galaxy, it was bigger than the Sagittarius. We know the Sagittarius galaxy brought in with it its own entourage of globular clusters. And so then there must be globular clusters that we can find that are associated with the Sausage galaxy. And so this is a plot from a paper by Guchil-Mayong. We're looking at apocenter versus pericenter using the wonderful Gaia proper motions of the globular clusters. And these are lines of constant eccentricity. So this is the most eccentric line, an eccentricity of 0.9. The color coding refers to the different types of globular clusters, the red being the most abundant, the old halo globular clusters. And so we're looking for an agglomeration of globular clusters that are moving on very eccentric orbits within about 10 or 20 kiloparsecs of the galactic center. And there indeed are the sausage globular clusters. There's more evidence, rather than just the eccentricity of these globular clusters, that they are associated with an early infall event. And this paper, the sausage globular clusters, describes that evidence. I'm going to show another plot now, which is the structure of the Gaia sausage. So far we've looked primarily in configuration space. So this is work by Iulianu Oio from Cambridge, and he's looked at the Ara-Lyra distribution of stars in the sausage, and we're plotting X versus Y, so this is a projection onto the galactic plane of stars in certain heights above the galactic plane. And so we say clearly what looks like a merger remnant, a triaxial structure, a clearly triaxial structure, and we can even associate some of the well-known clouds or agglomerations of stars in the stellar halo, the Hercules Aquila cloud or the Virgo overdensity, with this structure. But these are early days. There are lots of questions that remain unanswered. Is the merger responsible for the creation of the galactic disk and the Barron bulge? Remember, this would have been a gas-rich merger. This galaxy would have brought into the Milky Way with it a lot of gas. How much dark matter has this event contributed? And does the dark matter show similar behavior in terms of structure in velocity space as to the stars? Did the progenitor not merely bring globular clusters? Did it bring small satellite galaxies? This object clearly is of the side of the Magellanic Clouds, and we know that the Magellanic Cloud has a satellite galaxy, probably further satellite galaxies. Did the event produce the most energetic stars in the galaxies? And how can we use it to measure the escape speed from the Milky Way? And what is its structure? Where are the unmixed trails of stars that must have been created as part of the merger event? So I've given a brief introduction to Sausage-Mania. This is a rough chronology of some of the important papers. the paper by Vasily Belokurov and co-authors, which introduced some of the ideas, and then 2 fundamental papers by Guchel Mayong. There's also a very nice paper by Diedrich Kreuzen, Nate Bastian, and co-workers, who didn't use Gaia data at all, but looked at the properties of the globular clusters and concluded from the properties of the globular clusters that there must have been a similar set of sequence of events that gave rise. So they also argued for a very early set of merger events. And then there is a nice summary in Amina Helmi's paper, the formation of 2 of the major structural components of the Milky Way. Conclusions. I think revolution is used in the title, and I think we will find that the 25th of April 2018 was a revolutionary moment.
Ketchup involved?
Daisuke Kawata from MSSL. So this Amina Helmi's paper, they call Gaia enchiladas or something, and it's the same things. It was a Gaia sausage, and also the Derek paper. I think they are talking about 3 different sequences, and which one is a Gaia sausage? Or do you think it's Gaia sausage 1 galaxy or multiple galaxy? That's, if you could comment about that, that would be very helpful.
So you asked 2 questions there at least. So is the Gaia sausage 1 galaxy? I think that is hard to establish. You have to build a very, very strongly radially anisotropic component. You clearly can't do that by having lots of things merge from all directions. You've got to have things merging just from one direction. Right. The easiest way to do that is with one big clunker. Now, if you said, could it have been 2 things? One medium-sized clunker and then another medium-sized clunker falling in the same direction? I think that's very difficult to rule out. It could have been. So I think probably the easiest way to explain it is 1, maybe 2 big merger events. If there were 2 merger events, it would be something like the LMC and the SMC, 2 galaxies that are almost bound, falling in together. The second question refers to Gaia Enceladus and the Gaia Sausage. And I think that is a rather difficult question to answer. If you look at the spatial position of Gaia Enceladus as reported in the Helmi paper, that won't correspond to the Gaia Sausage. But I believe that is largely caused by the fact that they didn't make a proper accounting for some of the selection effects.
Is there any evidence from earlier kinematic data for this dramatic conclusion?
So that's a good question. I think from kinematic data, no. We've never had data of such remarkable quality. Nonetheless, there have been hints from radial velocity surveys that this might have been the case. So this is the old work on the dual halo that was put forward by Daniela Carola and Tim Beers based on radial velocity surveys. And there were also papers that looked at the structure of the stellar halo and saw that the stellar halo had a sharp break at 30 kiloparsecs. And of course, they conjectured that that was the apocenter of such an early merger event. And that is indeed correct. There is a sharp break at 30 kiloparsecs, and that is the apocenters of the stars that came in the Gaia Sausage. So there were hints, and so I think you could say that this idea was in the air, like all ideas. But it was really the Gaia data that have made the case, I think, unanswerable. It's very difficult to see how you would produce such a structure dominated by radial orbits, except by having an almost head-on collision.
Sorry, following up that, and in the 2003, with Chris Brook and Brad Gibson, we look at the Hipparcos data and comparing with our cosmological simulation, and we found this kind of features and published that in 2004, and we forgot about it. And and then he's looking at that in the Gaia Sausage, and we saw that.
You're
big
publishing
shape.
too much.
Yeah,
You're forgetting
however,
what's in your own work.
however, it's interesting history is, and again, Lindbergh Sandage, they show the color versus eccentricity, and there's some halo stars and having a sort of a high eccentricity blue stars. So even again, Lindbergh Sandage later, there is such kind of high eccentricity stars. Maybe they are related. So it will be interesting history.
Thank you. I didn't know about that.
Okay, I think it's time to finish. So I'd like to thank all our speakers again for a fantastic session.